So although we're encouraged to never engage in hypothesis testing where we reject or fail to reject a null hypothesis, it is still used, and so it is still important to understand some issues that come up. So that's what this video and the next are going to be about. In this video, we're going to focus on type 1 errors, and in the next video, we'll focus on type 2 errors and the power of the test, which we'll continue next class. So for right now, let's think about type 1 errors, and I want to define the size of a test, which is the probability of making a type 1 error. So the size of a test is the probability that you make a type 1 error. And as we think about this, I want to explicitly condition on the fact that the null hypothesis is true. So just to think about this for a second, if we make a type 1 error, we're in the first column of this table up here, and that is the column where the null hypothesis is true. So you can either just say it doesn't make sense to think about the probability of a type 1 error if the null hypothesis is false, or you could say the probability of making a type 1 error is 0 if the null hypothesis is false. Either way, it's not a very interesting thing to think about. So I want to focus on probability of making a type 1 error if the null hypothesis is true. And this will be mentally helpful as we start to calculate probabilities of things a little bit later on. So this is called the size of a test. And by definition, or it almost basically follows from the definition, the probability of a type 1 error, so the size of a test, is less than or equal to alpha. So this says that the size of a test is less than or equal to the significance level of a test. This is a statement that, I find it honestly a little bit confusing. I find it easier to see through examples than through a formal verification, although that can be done as well. So I want to take the route of just seeing why this is the case through examples. So the first example, I want to use the examples from last class. So the first example that I want to use is this one that we explored last class as our second example and then continued in lab 15. So this is a setting where we have x1 through x5 normally distributed with mean theta and variance 5 squared. And we want to conduct a test of the null hypothesis theta equals 25 versus the alternative theta equals 10. And in our example, we said, suppose that we observe x bar equals 20 based on our sample of 5 observations. So the thing that we did in the written part, and then we followed up on the lab, is we said that the likelihood ratio test for this is based on a probability that the sample mean is less than or equal to our observed sample mean. So in order to calculate a p-value, we need to find the distribution of the sample mean. So the first thing that we said was that x bar is distributed as normal with the value of theta from the null hypothesis and a variance that's 5 squared divided by 5, which gets you to 5. So this is the distribution of x bar if the null hypothesis is true, which is what's relevant for calculating a p-value. And then we need to calculate the p-value, and so we do that with p-norm. And then the first argument is 20, and the mean is 25. The standard deviation is the square root of the variance, so square root of 5. So this quantity is the probability that x bar, the sample mean as a random variable, is less than or equal to the observed x bar, given that the null hypothesis is true, which is what we showed was the way to calculate a likelihood ratio test for this example. And this p-value is 0.0127. So that's the setup that I want to work with in this example. So let's continue the example from lab 15. And just so that we have these statement on the notes, we have x1 through x5 distributed normal with unknown variance or unknown mean theta and variance 5 squared. And the null hypothesis was that theta is equal to 25. The alternative was that theta is equal to 10. And the p-value for the likelihood ratio test we've seen is the probability that x bar is less than or equal to x bar, given that the null hypothesis is true. So in a picture, the way that we just did that p-value calculation was like this. Here's a normal distribution that is the distribution of x bar, which is distributed as normal 25, 5, if the null hypothesis is true. And so what we did, so this is centered at 25, and somewhere about here maybe is the number 20. And we calculated the p-value as the area under the curve to the left of that, and that area was 0.0127. And that was the p-value. So this is as far as we went with this example the other day. What I want to do now is go one step further and say, suppose that I want to do a hypothesis test where I reject or fail to reject the null hypothesis. And there are going to be two approaches. To making this decision about whether I'm going to reject or fail to reject. The first of these is the way that we've set it up and framed it so far, which is to compare the p-value to the significance level alpha. And reject if the p-value is less than alpha. So in this case, our p-value was 0.017. And let's suppose that we're doing a test at the significance level alpha equals 0.05, because that is what is most common. So compare that to 0.05, and it's less than that. So we would reject the null hypothesis. That's one possible approach. Here's another possible approach. Instead of looking at the p-value, I'm going to compare my observed test statistic, x bar. So I'm thinking right here about the observed value of the test statistic. And I'm comparing that to a critical value, x bar. And the idea is going to be, we're going to reject the null hypothesis if the observed statistic is more extreme than the critical value. And I want these two approaches to be equivalent. So this means that in order to figure out what this critical value is, I'm going to need, so for this to work, for these two ideas to be equivalent, the setup is going to be that the p-value, if I'm going to reject the first one, I have to be able to reject using this first procedure, if and only if I also would reject using the second procedure. And so what that means is that the p-value is less than alpha, so that I would reject based on idea number one here. if and only if the observed test statistic is more extreme than the critical value. So if and only if my sample mean x bar, lowercase x bar, is more extreme than this critical value that I'm going to pick. So I'm going to reproduce this picture. Actually, maybe I can add it on to this picture. So this 20 on the left-hand side was my x bar, right? And that was associated with a p-value of 0.0127. So the idea here is, let's imagine what would happen if I had a slightly larger x bar. Well, if I had a slightly larger x bar, say it's 20.1, then I would move that to the right a little bit and add just a little bit of area to the area that goes into the p-value. So if I move x bar up just a little bit, the p-value increases a little bit, but it's still less than 0.05. And so I would still reject the null hypothesis. And now I imagine, what would happen if I increased my sample mean a little bit more? The p-value would get a little bit larger still. And so as you keep doing that, as you move x bar to the right, the p-value gets larger and larger, and eventually there's a space here, maybe it's about here, where the area to the left of that is equal to the significance level of the test. And then you would be at the first place where if you increased it a little bit more, the p-value would be just too big and you would fail to reject. So that's the idea. Here is going to be my critical value. And the idea of this critical value is that I'm choosing it so that the area to the left of it here is my significance level, which we're supposing is 0.05. So the critical value is the value of the test statistic so that the corresponding p-value would be exactly the significance level. And so the reason that this works is that if my sample mean is to the left of that, then the area to the left of the sample mean is smaller than the area to the left of the critical value. And so that means in particular that if the sample mean is to the left of the critical value, then the p-value must be less than 0.05. So I'm going to write those two observations on the next page. So the setup for this critical value is that it's the value. I'm going to rewrite everything up above, the test statistic, so that the p-value would be the significance level of the test. And so if written in terms of words, what this means is that the probability that you get a sample mean x bar that's more extreme than this critical value given the null hypothesis is true, is equal to alpha. So you're picking the critical value so that this is true. And then based on that condition, if you take a sample and you get a sample mean lowercase x bar that's more extreme than the critical value, then the probability of getting x bar more extreme than x bar must be less than alpha. I'm going to write that. And the reason for this is what we saw in the picture up above. Basically, if x bar, the point in black here, the number 20, is more extreme than the critical value, then the area to the left of it must be smaller than 0.05. And so we have a smaller p-value. Okay, so we have these two approaches to making a decision about whether we're going to reject or fail to reject the null hypothesis. One is based on a comparison of a p-value to the significance level of the test. And the other approach is based on a comparison of the test statistic to a critical value for the test statistic. And the critical value is like the transition point between rejecting and failing to reject the null hypothesis. Okay, all of this setup, the point of all of this setup is to understand the relationship between the size of a test and the significance level of a test. So the size of a test is a probability of a type 1 error, given that the null hypothesis is true. So a type 1 error is that you reject the null hypothesis when the null hypothesis is true. So I want to see how we can understand that in terms of these ideas for rejecting the null hypothesis. So probability of a type 1 error, this is the size of a test. Size of a test is defined to be the probability of a type 1 error given that the null hypothesis is true. And so what this means is the probability that we reject the null hypothesis, given that the null hypothesis is true. And I want to think about this probability of rejecting the null hypothesis in terms of this second idea of comparison of critical values, just because it's easier to think about probabilities in this way. So when do we reject the null hypothesis? If x bar is more extreme than this critical value. Or in general, it'll be the test statistic, but let's think about it in terms of x bar here. So we are going to, by the argument up above, we're going to reject the null hypothesis in the case when the sample mean is more extreme than this critical value. So the probability that we reject the null hypothesis is the probability that the sample mean is more extreme than the critical value. And now we can look at how we chose that critical value. The critical value was the value of the test statistic so that the p-value is the significance level. In other words, the critical value is the value so that the probability of getting a statistic more extreme is the significance level of the test, 0.05. So this is what we just said here. The critical value is the value of the test statistic so that the probability of getting x bar more extreme than the critical value is alpha. So this is alpha from the line up above. Okay, so all of this was to show that in this case, this works out to say that the size of the test is equal to the significance level of the test. Okay, so this was a somewhat informal justification of this claim for just this particular example. I want to also think about this for the other example. And just to remind you, the statement up here was that the size of the test was less than or equal to the significance level. And we just looked at an example where the two were equal to each other for this normal example. So now let's look at our second example from last class. And we will see that in that example, the size is actually perhaps less than the significance level of the test. So I want to pull out this example from the first example from last class. And so in this example, we had two distributions, and both were distributions over a discrete random variable x, which could be one of the integers 1, 2, 3, or 4. And the null hypothesis specified one set of probabilities for each of those possible values for x, and the alternative specified another set of probabilities for each possible value of x. And then we worked last class through finding the likelihood ratio for comparing the null to alternative hypothesis, as well as the p-values for the likelihood ratio test. So what I want to do now is to find the size of this test for a couple of examples. So let's suppose that alpha is 0.01. And this is going to be for our second example. So for this example, with this discrete distribution, let's suppose that we're going to do a test with a significance level of alpha equals 0.1. And based on this, I want to find what is the size of the test, which is what's the probability of making a type 1 error. So what's the probability of making a type 1 error given that the null hypothesis is true? So when am I going to make a type 1 error? I'm going to make a type 1 error if the p-value is less than or equal to the significance level of the test. So probability of type 1 error is equal to probability that the p-value is less than or equal to alpha, given that the null hypothesis is true. And so in this case, this is the probability that the p-value is less than or equal to 0.1, given that the null hypothesis is true. So if you look over here in this table on the left-hand side, you see that the possible p-values that we arrived at were 0.7, 0.5, 1, and 0.2. So none of those p-values are less than 0.1. So there's a probability 0 of getting a p-value less than or equal to 0.1. Okay, so this is an example where the size of the test is 0, but the significance level is 0.1. So it could happen that the size of the test would be less than the significance level of the test. And the way that this happens is if your distribution is discrete. So with a discrete distribution, you can get a size that's less than the significance level. I want to have one more example of a significance level and a size of a test with this example. So here, let's suppose that alpha equals 0.3. And again, I want to find the probability of a type 1 error. So the size of the test. So this is now going to be probability that the p-value is less than or equal to 0.3, given that the null hypothesis is true. And so here I'm looking over at what are my possible p-values, and there's only one of them that's less than or equal to 0.3. So this is going to be probability that the p-value is equal to 0.2. And I'm calculating that probability based on the condition that the null hypothesis is true. So the probability of the p-value of 0.2 is the same as the probability of getting x equal to 4, which according to the null hypothesis is 0.2. All right, so that is examples of the size of a test.